Okay, so I'm Oscar Paulo. I'm the chair of this session. So our first speaker is
Shall I start? Shall I start? Do you hear me?
You just start. Mute. Oh, sorry. Yeah.
I'm sorry, my voice was muted.
I didn't hear what you.
Yes, please start.
Okay, I shall start. Do you hear me well? I hope you hear me. Do you?
Yes, fine. Yeah, you are supposed to
Okay.
hear.
Shall I start?
Yeah.
Okay, so I shall present a paper of mine, my paper on semantics of propositional attitudes in type theory of algorithms. Briefly on the outline, so I intend to present in more details the points, the sections 1 and 2. And the reduction calculus is quite longish, the formal. So I'll present most of it with examples, but I will present the two new kinds of rules. Actually, there are three new rules: the compositionality rules for the attitudes and the scope rule for the attitudes, and how they propagate into the entire system of the reduction rules. And I also will point to some theoretical features of the type theory of acyclic recursion, but I'll mention here and there also the full recursion, the type theory of the full recursion. So in the general picture of the type theory of algorithms, it's the initials, just to say briefly on the historical points, this theory appeared quite long ago, but it took years to take up, and now in the last years I'm trying to progress on it. So the distinctive features are that this type theory in both versions, in the full recursion and in the acyclic recursion, is that it offers very special syntax which extends the classical simply type theory of lambda calculus. So it is much broader and it's proper extension. And the distinctive feature is that it offers two kinds of semantics. The denotations simply just follow the traditional denotational semantics of any logic language. So it follows the definition of the denotation function of the formal language, follows the structure of the terms. So everything goes there, the denotational semantics by induction on the terms. The new features, it encompass the recursion theory inside of its formal language. So traditionally, recursion theory is a mathematical structure at the semantical level. So here it is both syntax and semantics, and there is a interface between syntax and semantics of the recursion theory. So also a new feature is that, which means that the algorithms for the computational semantics, the theory offers a very pleasant feature, especially for the natural language, acyclicity algorithm. So there is a criteria, a special restriction on the syntax, so that this restriction guarantees algorithms that are closing off after finite number of steps. Of course, the theory allows also full recursion. That's important for programming semantics of the programming languages and for the compilers of the programming languages, but also for the extension that I'm talking today, introducing for the attitude. So we all know that knowledge and belief and statements, they have self-references, and that is modeled by full recursion. But I will not talk about it. I'll focus on the acyclicity because that's important. So how is this interface provided? Between algorithms in the level of the syntax and the denotations that is provided by special reduction calculus of the theory. So there is a minimum 10 rules, plus I'm adding already quite many, 4, 5, 6 up to now, additional reduction rules to bring more power, more expressive power, especially for the semantics of natural language. So the reduction calculus is effective. There is a theorem. If I end to it, in the theoretical results, I'll formulate it precisely, but roughly, intuitively, it is for every term in the formal language of the theory. There is a corresponding unique up to congruence canonical form, and the reduction calculus is effective because after finite number of steps, it guarantees obtaining of the canonical form. In general, without the extensions that I have been adding, it's quite complex. The complexity is quite, at certain points, it's not so good. So actually, I'm trying also to introduce these new rules, new reduction features, so that the complexity gets more better for the natural language. So now, what is the algorithmic semantics? For every term, there is a canonical form. And for special kind of terms that have meanings, algorithmic meanings, because not all terms have such meanings, for those terms, and they are the important ones, for each one of them, there is a algorithm for computing its denotation, and this algorithm is determined by its canonical form. What is the placement of this type theory in the class of the simply type theories that include lambda calculus? So it is proper extension of Montague intensional logic. So everything that was done in one or other version of Montagovian intensional logic is included in the language of the algorithms. It also extends properly Gallin type system, and actually Gallin type system extends Montague intensional logic, and that is also important because Gallin type theory allows at the syntactical level states, which is important for the intensional semantics. So all this goes into the formal language. In Montagovian intensional logic and grammars, those are external, the possible words. They are in the primarily, there are no variables and no other ways to describe the possible worlds in the formal language of the Montague intensional logic. So Gallin, he introduced it for the first time with variables, and this is proper extension of including those special terms with states. That's important to represent pragmatics and agents, speakers, listeners, participants in the denotation, semantical representation at the syntactical level. So in this paper today, I shall add to the syntax expressions, formal expressions of propositional attitudes, including statements. And in order to get the proper algorithmic semantics, I introduced two special operators at the syntactical level, just like lambda is a syntactic operator, quantifiers, logic quantifiers, logic operators, they are at the syntactic, present also at the syntax and the semantics. So I include them here too. And why I have two, this I have never seen such operators, but they help me to represent. So we know all that natural language is hugely ambiguous, and a huge contributor to the ambiguity is the quantifier scopes. And then the attitudes also add more semantic ambiguity between scopes of the attitudinal expressions and their semantics. So here I manage with these two operators to represent both at the syntactical level and also at the semantical level, the underspecified attitudinal scopes, and from the underspecified attitudinal scopes to derive specific scopes depending on context, depending on specific states. Also, I introduce rules that the reduction rules that will guarantee also that these operators and the attitudinal expressions in the terms, at the level of the formal terms, they also can participate in the algorithmic semantics via canonical forms. So here is, I probably have been telling this so many times that, but probably some of you don't know it. So this is syntax. This type theory has syntax which is typed at all of its levels, in the levels of the constants, the levels of the variables and the terms. Every expression is typed, and the types are just like in Montague, intentional logic, except the blue. So Montague didn't include types, primitive types, basic types for states, for the possible world. So these are included here. Of course, Montague intentional logic has expressions without special operators up and down for intension and extension inside of the term structure, but it doesn't include variables and more complex expressions of including this special type and variables of this type. And this is very important also for today representation of the distinction between underspecified and specified scopes. So here, instead of getting too clumsy in Montegovian intentional types from states, from possible worlds to other types, I use this special abbreviation, which helps readability. So the new feature, which helps together with the reduction calculus, is the division of two kinds of variables. Not only that the variables are typed, but also there are two kinds. Pure variables are those that we know, which present in any lambda calculus for quantification and lambda abstraction. But here we also have recursion variables. I call them also memory variables because they play very important role for saving calculations and for saving values of the results of the calculations. And this is a brief representation of the syntax of the terms. So the new the terms in black are the classical terms for constants, variables here of both kinds. So they also are terms, the application terms and the lambda abstraction terms. So the new thing is in the blue is that the lambda abstraction terms as well as quantifiers here, they are allowed only at the level of the pure variables. The new terms that represent recursive the recursion and the recursive computation is 4b. It looks, these terms, they look like let expressions, but they are essentially different from the let expressions. So in the previous paper, in a previous last year from the paper, in the extended paper, I included a formal proof, a mathematical proof that recursion terms extend the let expressions. So here, the important thing is that in this special set of the assignments, these are the computations and saving values of computations in memory locations. And then, of course, just similar to the let expressions, they are used those values to compute the denotation of the entire term. So there is also one more kind of terms which I don't have time to present here, but in the extended paper I'll present them. These are terms with restrictor. So 4b, this kind of terms, they correspond to the recursion theory, and the restrictor terms, they correspond to the mu operator in the recursion theory. So how much time do I have? So for F and G, these are the new terms, and here informally, which goes through the entire talk, this is one of the operators to scope. It applies over a term, and this means that the term B is candidate to be scoped, whatever is in this term, to be distributed in a closed term or outside of the closed term, and that is the job of the rules. So G-C operator is the closure. As long as to scope, there is a rule that transforms the scope B into closed term, and some of the parts of the term B are moved out, then the scope is decided and closed and cannot be anymore opened. So acyclicity constraint, I shall skip it, but it is the one that guarantees the acyclicity portions of the theory. So here is a simple example of a sentence which includes, I'll include detailed explanation of the possessive noun phrases. So here actually the important is that the canonical form of this sentence is 4e. So this is actually the algorithm for computing the denotation of the sentence 8a. And here now, in the next example, I shall represent how it goes inside of the scoping, inside of the scopes of belief statement, but it goes also for all attitudes. So here, if we have a sentence like 9a, so there are many possibilities and options, but here is one possibility, this sentence to be rendered into a term A1. And here is what it tells. So beliefs is the constant which translates the verb beliefs, and it applies to what is supposed to be its scope, but it's still open. And J is the one who believes, the believer. So here, why I use to scope? Because, so happy Mary's sister, this is the translation of the sentence, Mary's sister is happy. This is the term. So not everything is from this term is inside of the beliefs of the believer Jim. So that's why this scope, this term is open. It is candidate to be closed entirely, but it also allows some portions of it to be moved out of the scope of the believer. So, for example, here the canonical form is 9D, and 9D is already to scope. This term is reduced to a recursion term, and portions of it can be moved out from the scope of the operator, the scopic operator. And this happens in two different ways. So to-scope gets transformed into the closure operator by special rule, and we get two different readings. So in the dedictive reading, Mary and sister are inside of the believers in Jim's beliefs, and in the Dere, they're already outside of his beliefs. So Jim here just believes that an individual MS is happy, but Jim doesn't know that this individual is named Mary, and Mary is the reference to the individual. The name Mary is the reference to the individual denoted by the constant Mary of the speaker. So here is okay, I'm done. This is the general pattern for not only for beliefs, etc., and Mary and Jim, but for the entire class of attitudinal binary verbs. How much time do I have? No time. 10 minutes. So probably for the question. Okay, I shall stop here because this is actually, this slide is the general algorithmic pattern. So actually just briefly to say, by introducing these two operators, I allow both multiple scopings and specific scopings and of the attitude expressions. But also by this general algorithmic pattern, there is even more efficiency because the general pattern 13A and B and C, actually 13C is the pattern, the rendering pattern is psi and phi are natural language expressions. Then here we have an underspecified term, which represents a huge class of possibilities, both from the verbal side and from the scopal side. So this is what I wanted to say, the major things. But I left in the slides more details if you are interested to look at something. So this is what it is.
Thank you very much. So, about 7 minutes for discussion. Do you have any comments or questions for this room and in the Zoom? Okay, please think about question. Okay, so I have a very simple question. So you have a sentence. John believes that yes, sister was. I forgot the example, but you have a sentence like a belief sentence. You have,
I don't hear well. Maybe you can, because somehow the voice is cut off into pieces. Perhaps you can try again to repeat somehow more closer to the speaker or
now it's
microphone.
Can you hear me? Can you hear my voice?
Yes, now I hear better.
Okay, yeah. You have an example like John believes that Mary's sister is something, and so you have a scope theory, but you also have a presupposition like Mary's sister, and in your theory you don't analyze this presupposition. The possessive S, Mary's sister, has a presupposition that Mary has a sister, right?
Yes, here it is.
Yeah. Oh, you have a, okay. Which part is a presupposition and which part is an assertion? You have
the presuppositions. Okay, I'm sorry. So actually, I didn't touch the question about the presuppositions. So you are asking about presuppositions.
Yes.
I didn't touch this. This is for, actually, this is what I'm targeting, and not only presuppositions, but also kinds of inferences, semantic inferences, to be represented syntactically. So that is going to be contributed, according to me, already by the syntax semantics interface. Let me show you. I think I have included a picture somewhere. Yes, here. So here there is a natural language syntax, and there is a rendering translation into the terms, like Mary's sister. So here, by natural language syntax, I mean generalized syntax, which will include not only syntactical rules at the level of the syntactical structure of sentences, but it will include also morphological analysis, and major parts of the semantical representations in these terms is contributed by the lexicon, by the lexical semantics. And there, sister, which is the common noun, should interact with the possessive, and the possessive should carry this presupposition inferences, and not only that, but also for time, for the verbs, time and space. So then actually here, when we have here semantic analysis, let me show here this, I'll write this more into the paper. So actually here, this apostrophe, this is Mary's with apostrophe, this is a term, but actually a pseudo term. It is abbreviation of, this is its full term. So relation to Mary, it takes another yet relation, and the value should be individual, which means that after I add, it is here somewhere, so Mary's sister already, Mary's sister, it will be one of the individuals that is sister of Mary. There might be more of one. It's not a definite unique one. There might be more. So actually what you are asking me, is there some presupposition that will infer that Mary has a sister? So this will be contributed by this special relation to, and in its interaction with Mary and with sister, but mainly it will be with sister, because not only not all properties here they have such presuppositions. So this will be contributed according to, I haven't worked on it, but this is my idea.
Okay, thank you very much. Okay, sounds nice. Yes. Okay, we have 3 minutes. We have questions or comments? If not, then maybe, yeah, we can stop here. And by the way, I haven't looked at the comments.
This question to me, because I didn't hear the last words.
We have one more question. Sorry. Yeah.
Okay, I like your question very much.
Can you hear me?
Yes.
Thank you. So could you go back to the slide where you introduced the distinction between dedictor and Darrow readings?
Oh, okay. Here.
Yeah, here, so you show 2 representations, but how do you obtain these 2 distinct readings?
Here, actually, yes, I'll show you. There is a special rule. I included in the rule, system of the reduction rules. Let me see where. Yes, just here it is scope rule. So here it is. So there is a formal rule that says you saw that actually the translation from the natural language includes this operator, and inside here it's scope. It applies to the translation of the attitudinal, the complement of the belief. And then here it is underspecified. Here we don't know whether this is the dicta or the re, because this is open, undefined scope. And this rule moves out a selection. So these are sets of assignments. So it moves parts of the assignments outside of the scope of the closure operator, and those that are closed are inside C. And after this is done, this is the scoping. And how actually, in what way, magical or what? So take a look. I didn't talk about it, but take a look. So to scope applies not only to the translation of the attitudinal complement, but also to this is a pragmatical thing, to the scope, to the context, to the state, or to the situation. And then also, depending after this application, take a look here. So actually, this goes inside, apply to be 0, but it can be different. So actually, this is the machinery. And that's it.
Okay, so let's thank our speaker.
So what shall I do now?